Assalamu alaikum. Dear students, today we will learn power amplifiers. What are power amplifiers? Power amplifiers are basically the amplifiers that perform both current and the voltage amplifications. For example, in bipolar junction transistors, common emitter amplifiers are the power amplifiers. Why? Because common emitter amplifiers perform both the current amplification and the voltage amplification as well, while a common base amplifier only provides the voltage amplification. Similarly, common collector amplifier uh, provides only the current amplification. So in this way, power amplifiers are those amplifiers that provide us both the current and the voltage amplification. So there are four types of power amplifiers, namely class A power amplifier, class AB or B power amplifiers, class C power amplifiers, and class D power amplifiers. So coming to the first power amplifiers, class A power amplifiers are basically those power amplifiers that basically provide output for the entire 360 degrees, and therefore their efficiency is about 25%. So you can see in figure 12.21 that the output waveform is drawn for the entire 360 degrees. So in class A power amplifiers, output is provided for the entire complete cycle for the complete 360 degrees, but the efficiency is poor, so it's about 25%. Similarly, if we talk about the class B power amplifiers, here the output waveform is basically provided for half of the cycle. So it is for either for positive half cycle or for negative half cycle. So therefore, uh, the efficiency of class B power amplifier is somewhat better than the class A power amplifier. Similarly, for class C power amplifier, uh, the output is basically between, uh, you can say, uh, 180 to 360 degrees. And for the class D power amplifiers, since the output is in uh, pulses, so it is a much efficient power amplifier. So uh, these features are basically summarized in table 12.1. So you can see for in table 12.1 that for class A power amplifiers, the output is for the complete 360 degrees, but the efficiency is poor and it is between 25 to 50%. Similarly, for class AB power amplifier, the output is between 180 degrees to 360 degrees, and therefore the efficiency is between 25 to 78.5%. Uh, Similarly, for class B power amplifier, the output is for 180 degrees and the maximum efficiency is about 78.5%. Similarly, for class C, the output waveform is available for less than 180 degrees and therefore their efficiency is better than class B power amplifier. And since in class D power amplifiers, the output is more than output is for small pulses, the output is there. Therefore, their efficiency is much greater than uh, the previous three types of power amplifiers. So its efficiency is about 90% or more. Now, how can we basically identify that what is the efficiency of a power amplifier and how can we calculate those efficiencies. To understand this thing, it is a very simple uh, thing to understand. Basically, uh, in a power amplifier, the input power is basically the DC bias we provided to the amplifier, while the output power is the AC power that we receive at the output of the transistor or amplifier. So the efficiency is basically uh, PAC divided by PDC multiplied by 100%. So in any configuration, if we can calculate the DC power provided to it and the AC power we are taking as output, then the ratio of PAC and PDC multiplied by 100% will basically give the efficiency of the power amplifier. Now we start the first configuration, that is class A power amplifier, which is series fed. So you can see, as I told you earlier, that common emitter amplifier is the simplest and the easiest possible power amplifier. So you can see that in this figure 12.2, we are having a common emitter amplifier. And if we calculate its base current, then to calculate its base current, what we will do, we will apply uh, Kirchhoff's voltage law into its input side. That is, we will write minus VCC plus IBRB plus VBE equals to 0. And then we will make IB the subject of the equation, and it will become VCC minus 0.7 whole divided by RB. Now, after calculating the input current, that is the base current, we can easily find the output current, that is the collector current, using the basic relation, that is the collector current IC is equals to beta time the input current or the base current IB. Now to calculate the DC bias point, we need to calculate the VCE of this configuration, as we all know that it is a common emitter amplifier. So the bias point will be VCE comma IC. That is the output voltage VCE will be the x coordinate of the quotient point or the bias point, and the IC, that is the collector current, will be the y coordinate of the quotient point. So after calculating IC, we can easily find VC by writing a KVL on the output loop of the configuration. That is, we can write like minus VCC plus ICRC plus VCE equals 0. And hence we can make VCE the subject of the equation, and it will become equation 12.3. So after calculating this bias point, what we will do, uh, we will basically draw the output characteristic curve that is being drawn for you in figure 12.3. And then we will draw the load line using equation 12.3. How can we draw the load line? It is very simple. In equation 12.3, if we put IC equals to 0, then we will get VCE equals to VCC. So one point will be VCC comma 0. That is on the x-axis, that is the VCE axis. Similarly, if we put VCE equals to 0, then we will get IC equals to VCC upon RC, which is also known as the saturation current of the BJT. So we will simply get the point 0 comma VCC upon RC. Using these 2 points, we can easily draw this load line. Now the point of intersection of this load line and the output characteristic curve is basically the quotient point. So hence we can easily identify that whether our transistor is in the amplification region or in the saturation region or in the cutoff region. So obviously, if we are to use this transistor as an amplifier, so we will definitely use it in the amplification region. Now coming to the AC operations, It is a very complex figure here, and it is quite difficult to make you understand that how we basically draw the input signal and the corresponding output signal. I just give you an idea that what happens that first of all we draw the output characteristic curve using the specification of the transistor. Then we draw the load line using the output equation discussed a bit earlier. After drawing this output characteristic curve and the load line, we select a point as our quotient point. Like in this figure 12.4a, you can see that a dot is representing the quotient point. Now, this quotient point is basically determining whether the transistor is in amplification region or in the cutoff region or in the saturation region. So right now, the position of this dot, that is the quotient point, clearly mentions that it is in the amplification region. Now, how the output is drawn? It is basically a transverse curve of the input signal and the load line. So from the input signal, we come towards the load line, and from the load line, we basically come towards the output signal, and hence we basically draw this transverse curve. So it is a bit complicated to understand that what is a transverse curve. But fortunately, in our calculations, in our uh, gain calculations, and in our efficiency calculation, it is never required to basically use the transverse curve. It is this figure is basically given just to give you an idea that how can we identify that the output is drawn uh, completely or partially. So you can easily see that for the entire input signal, positive half cycle and the negative half cycle, we are getting complete output wave, complete half and positive half and the negative half cycle. Why it is inverted? For the positive half cycle, it is given negative half cycle, and for the negative half cycle, it is given positive half cycle. Because in a common emitter amplifier, there is a 180-degree phase shift between the input and the output signal. So hence, it is justified that it is a class A power amplifier because the output is available for the entire 360 degrees, and it is a common emitter amplifier. So the output is having a 180-degree phase shift from the input signal. Now coming to the power considerations, since uh, input power or the DC power is basically VCC time ICQ. So we can write it like PI equals to VCC into ICQ, where ICQ is basically the collector current at the quotient point. Now, output power, which is an AC power, is basically VCE RMS times IC RMS. So we can write it like IC square RMS into RC as well, or we can write it like VC square RMS upon RC as well. All these three are valid expressions for the AC power. Now, to calculate the efficiency of this class A power amplifier, what we will do, we will simply use the formula PAC upon PTC multiplied by 100%. What is the maximum efficiency? For maximum efficiency, VCE peak to peak can be equals to VCC, or maximum IC peak to peak could be equals to VCC upon RC. So therefore, if we take the first expression, so maximum power AC equals to basically VCC multiplied by VCC upon RC upon 8, and hence maximum AC power is VCC square upon 0.8 RC. Now to calculate the DC power, it is VCC into ICC upon 2. So therefore, it is VCC square upon 2 RC. Now to calculate maximum efficiency, we will divide this P out AC with P out P in DC, and hence we will get uh, all other things are being cancelled with each other. That is, VCC square will be cancelled by VCC square. Uh, RC will be cancelled by RC, and hence we will get only 2 by 4 multiplied by 100%. That is, sorry, 1 by 4 into 100%. That is 25%. So what was the conclusion? That for a class A power amplifier, the maximum efficiency is basically 25%. Now take an example. In example 12.1, they are saying calculate the input power, the output power, and the efficiency of the amplifier using figure 12.5 for the input voltage and the result that results in a base current of 10 milliampere. So first of all, what we will do, first of all, we will calculate the base current using minus VCC plus IBRB plus BB equals to 0, and hence VCC minus 0.7 volt divided by RB will be IBQ. So IBQ is 19.3 milliampere. Now to calculate IC, what we will do, we will multiply this IB with the beta, which was given in the figure as 25. So ICQ will become 0.48 ampere. Now to calculate VC, we already proved the equation that it is VCC minus ICRC. We know IC, we are given RC, and we are given VCC. So hence VCEQ is 10.4 volts. Now this is the bias point that we are having. Now for maximum what efficiency, what we could do, VCE must be equals to VCC, that is 20 volts, and IC must be equals to VCC upon RC, that is 100 milliampere. 1000 milliampere, that is 1 ampere. So using these facts, we calculated the AC power as IC square RMS into RC, and we got it like 0.625 watt. Similarly, for PDC, we wrote it like VCC into ICQ. So VCC was 20, ICQ was 0.48, and hence we got 9.6 watt. Now for efficiency, it's PAC upon PDC multiplied by 100%. So we got the answer as 6.5%. So the conclusion is that the maximum efficiency of a class E power amplifier is 25%, while for practical circuits, it is less than 25%. For class A power amplifier, the output is available for the entire duty cycle, for the entire 360 degree. But for class A power amplifier, uh, we have uh, much less efficiency as compared to the other classes of the power amplifiers. Why? Because output, we keep the output available for the entire duty cycle, and hence it uh, basically uh, due to this entire 360-degree output voltage, what happens that the output power becomes smaller as compared to the input DC power, and hence the efficiency is reduced. So inshallah, in the next lecture, we will study the transformer coupled class A power amplifier, which is a bit better than the class A power amplifier in terms of efficiency. So till then, take care and Allah Hafiz.